Summer, 1942. Minneapolis, Minnesota. On the top floor of a flour mill owned by General Mills, behind locked doors and military secrecy, one of the strangest weapons programs of World War II is underway. Inside, engineers and psychologists are not working on radar or rockets. They are training pigeons. This is not a joke. This is not a legend. This is Project Pigeon, a classified American weapons program designed to solve one of the most dangerous problems in modern warfare: how to hit a moving ship with a falling bomb. To understand why the US military even considered such an idea, we need to understand the situation facing Allied forces in the early years of World War II. The problem was simple to describe and nearly impossible to solve. Ships move. Bombs fall. A bomb released from 15,000 feet follows a predictable ballistic path. A warship under attack does not stay still. By the time a bomb reached the ocean, a maneuvering ship could be hundreds of meters away from its original position. The results were catastrophic. Against maneuvering naval targets taking evasive action, conventional bombing achieved hit rates below 5%. In many cases, accuracy dropped close to zero. Massive bombing raids often produced nothing more than splashes of water and wasted fuel. Germany solved this problem first. In 1943, the Luftwaffe introduced the Fritz X, the world's first operational precision-guided bomb. The Fritz X was radio-controlled. A bombardier inside the aircraft visually tracked the falling weapon and used a joystick to steer it onto the target. Its effectiveness shocked the Allies. At Salerno, a single Fritz X struck the British battleship HMS Warspite. The bomb penetrated 6 armored decks before exploding deep inside the ship. Warspite survived, but barely. She was crippled for months and missed the D-Day landings entirely. The message was clear: guided weapons were the future. The United States rushed to develop its own guided bomb programs, but radio guidance came with a fatal weakness. Radio signals could be jammed. The same transmissions that guided a bomb could be detected, interfered with, or overwhelmed by enemy countermeasures. Early electronic systems were also fragile, vulnerable to vibration, heat, and mechanical failure. What American military planners wanted was something radically different. A guidance system that tracked targets visually required no radio emissions, could not be jammed, worked reliably under extreme conditions. And that is where B.F. Skinner enters the story. Burrhus Frederick Skinner was not an engineer or a physicist. He was a psychologist at Harvard University, already famous for his work on learning and behavior. Throughout the 1930s, Skinner had pioneered the study of operant conditioning, the idea that behavior can be shaped through systematic reward. His experiments demonstrated that animals could learn extraordinarily complex behaviors if trained correctly. A pigeon, Skinner showed, could be trained to recognize specific shapes, track moving objects, maintain intense focus for long periods, repeat precise actions thousands of times. Pigeons also possessed something early machines lacked: remarkable visual processing and motion compensation. They could track objects smoothly while moving themselves, a task that challenged even the best early control systems. In 1940, watching pigeons near a train station, Skinner had a thought that initially sounded absurd even to him. What if a pigeon could guide a bomb? Skinner began small. He trained pigeons to peck at projected images on a screen. When the pigeon pecked the correct image, it received food. Over thousands of repetitions, the birds learned to track targets with astonishing accuracy. Then came Pearl Harbor. December 7, 1941 transformed Skinner's curiosity into a military proposal. He approached the National Defense Research Committee with an idea that sounded like madness. Place pigeons inside guided bombs. Train them to recognize enemy ship silhouettes. Let them steer the weapon visually all the way to impact. The committee reacted with skepticism and disbelief. But desperation has a way of lowering barriers. Precision guidance was urgently needed, and existing solutions were failing. In June 1943, Skinner received a formal contract. $25,000. Adjusted for inflation, nearly $500,000. The contractor chosen was not a weapons manufacturer. It was General Mills, the breakfast cereal company. General Mills had advanced research facilities and engineers experienced in designing precision mechanisms. Their vice president of research, Arthur Hyde, agreed to support the project as a public service. A flour mill in Minneapolis was converted into a classified laboratory. Psychologists trained pigeons. Engineers built control systems. Security was tight. Skinner brought along graduate students who would later become major figures in psychology, including Keller Breland, Marion Breland, Norman Gutman, and W.K. Estes. The goal was simple but unprecedented. Turn a living animal into a real-time guidance system. And against all expectations, it worked. By the end of the initial training program, Skinner had trained 64 pigeons. According to his later published accounts, not a single bird failed. No washouts. No dropouts. Every pigeon qualified. They tracked moving targets under simulated flight conditions, noise, vibration, and physical stress. They maintained focus for extraordinary lengths of time. Some pecked continuously for nearly an hour without losing accuracy. The results astonished the engineers who saw them. But convincing engineers was not the real challenge. Convincing generals would prove much harder. Training pigeons was only half the problem. Even if a bird could recognize an enemy ship and track it visually, the real challenge remained. How do you translate a pigeon's pecking into precise mechanical control of a falling weapon? Skinner's answer was both simple and ingenious. The guidance system developed at General Mills was built around a test vehicle known as Pelican. Inside its nose cone sat the heart of the experiment, a biological guidance computer. Instead of one pigeon, Skinner used 3. Each bird was placed in its own small, pressurized compartment. In front of each pigeon was a translucent circular screen, 4 inches in diameter. At the very front of the nose cone, a lens projected the external view, sea, sky, and target, directly onto the screen, much like a camera obscura in reverse. The pigeons had been trained through thousands of trials to peck at the silhouette of an enemy warship. As long as the target remained centered on the screen, all 3 pigeons pecked at the middle. The missile flew straight. But if the image drifted even slightly off-center, the system reacted instantly. Behind each screen were 4 pneumatic air valves, positioned at the top, bottom, left, and right edges. When a pigeon pecked, the impact momentarily opened the valve beneath that point. Air flowed through pressure-sensitive membranes called timbers, creating a signal. A venturi cone mounted on the missile's exterior continuously exhausted air. When pecking became uneven, for example, more pecks on the left side of the screen, the pressure imbalance displaced the membranes. That displacement was transmitted mechanically to servo-controlled steering fins, correcting the missile's trajectory. No electronics. No radio signals. No emissions to jam. Just air pressure, mechanics, and animal behavior. The use of 3 pigeons was not redundancy, it was design philosophy. Skinner created what he called an analog voting system. Each pigeon generated its own guidance input. The combined output of all 3 determined the missile's steering corrections. If one pigeon became distracted or made an error, the other 2 overruled it automatically. If multiple potential targets appeared in view, the pigeons tended to converge on the primary trained silhouette. A dissenting pigeon was outvoted, its incorrect pecking diluted by the correct inputs of the other 2. Skinner dryly described this as the punishment of minority opinions by mathematics. The system worked. And it worked far better than anyone expected. During simulator tests, pigeons tracked targets with over 90% accuracy. They maintained focus under conditions that destroyed early electronic components, vibration, noise, sudden movement, and rough handling. One pigeon pecked more than 10,000 times in a single 45-minute session, maintaining continuous target lock the entire time. That is nearly 4 pecks per second for almost an hour. Another bird held a simulated missile locked onto a street intersection for 5 uninterrupted minutes. No wandering, no loss of attention. Perhaps most impressive of all, pigeons tested years later, long after the project had ended, performed just as accurately without any retraining. Their conditioned responses had become effectively permanent. Engineers took notice. At the MIT Radiation Laboratory, one of the most advanced electronics research centers in the world, a servo specialist observed a demonstration of the pigeon guidance system. After reviewing the tracking data, he reportedly declared that it was better than radar by several measures relevant at the time. He wasn't joking. Radar guidance systems could be jammed. Vacuum tube electronics failed under stress. Pigeons did not. They were self-repairing biological systems, capable of operating in environments that killed early machines. The final demonstration was meant to silence any remaining doubts. A pigeon had been harnessed in the guidance apparatus for 35 hours prior to the test. During the live demonstration, It pecked energetically and continuously at the projected target. At one point, a scientist deliberately passed his hand through the light beam, blocking the image. The pigeon stopped pecking instantly. When the image reappeared, pecking resumed in a fraction of a second, faster than most electronic systems of the era could respond. Technically, the demonstration was a complete success. Psychologically, it was a disaster. Skinner later recalled that watching a live pigeon perform its task so perfectly only reminded the observing committee how utterly ridiculous the entire idea looked. The bird did exactly what it was trained to do, and that was the problem. The spectacle of a living animal steering a bomb overwhelmed the data. No amount of graphs or performance metrics could overcome the mental image forming in the minds of senior decision-makers. Skinner noted that the meeting was marked by restrained amusement, polite, professional, but unmistakable. The physics had won. The psychology had lost. After the demonstration, Arthur Hyde, the General Mills executive who had supported the project, gave Skinner blunt advice. Go out and get drunk. By early 1944, the decision was official. The National Defense Research Committee declined to extend the General Mills contract. The official explanation was that further work would delay other projects with more immediate promise. Unofficially, the problem was simpler. The generals did not believe in pigeons. Some technical issues remained unresolved. The mechanical linkage between pecking and control surfaces needed refinement. Security compartmentalization had also crippled development. Engineers at General Mills were denied full access to missile specifications, forcing them to design interfaces in the dark. But none of these problems were fatal. What killed Project Pigeon was disbelief. The idea worked, and that made it unacceptable. Although the Army's National Defense Research Committee cancelled Project Pigeon in 1944, the story did not end there. The United States Navy recognized the value of Skinner's idea, a guidance system that was immune to radio jamming and capable of operating in conditions that destroyed early electronics. In 1948, they revived the program under a new name, Project ORCON, short for Organic Control. The Navy version incorporated several important improvements. The old pneumatic valve system, ingenious as it was, had limitations. It relied on air pressure differentials, which could be affected by vibration, temperature, and mechanical wear. For ORCON, scientists replaced the pneumatic system with direct electrical sensing. Gold electrodes were attached to the pigeon's beaks, which contacted a semiconducting screen inside the nose cone. Each peck produced a clear electrical signal, instantly transmitted to the missile's steering mechanism. This eliminated air-based linkages entirely and made the system faster and more reliable. The Navy's ORCON tests were rigorous. Pigeons were exposed to combat simulation footage, high-speed motion, vibrational and acoustic stress, environmental extremes. Time after time, the birds excelled. They accurately tracked ships, coordinated steering signals through majority vote, and adjusted to changing targets, all in real time. In one test, pigeons successfully followed high-speed attack patterns projected on film, maintaining perfect focus for minutes at a time. Each bird performed consistently, demonstrating the same operant conditioning principle Skinner had perfected at Harvard and General Mills. For the Navy, the results were tantalizing. They had a guidance system that could outperform unreliable electronics, resist jamming, self-maintain without extensive calibration. Yet, once again, human psychology interfered. While the system worked flawlessly in demonstrations, it still involved birds pecking inside a missile. For decision-makers, that image remained absurd, even decades after Skinner's first tests. Project ORCON continued experimentally until 1953, when electronics finally caught up. By that time, electronic guidance systems were fast, reliable, and immune to many vulnerabilities that plagued early devices. The Navy formally ended ORCON, but the research was far from wasted. The lessons from Project Pigeon and ORCON went in multiple directions. One was touchscreen technology. The semiconducting screens used to detect pigeon pecks directly inspired early touch input systems for radar and targeting displays. Operators could designate targets by touching the screen, a concept that traces its roots directly back to a World War II weaponized pigeon program. Another was in behavioral psychology and animal training. The method Skinner and his team refined, shaping complex behaviors through successive approximations, became the foundation of modern applied behavior analysis. After the war, graduate students like Keller and Marion Breland applied these principles commercially, training animals for theme parks, television, and advertising. SeaWorld dolphins, circus animals, and television performers all benefited from techniques originally developed to turn pigeons into weapons. While American military planners struggled with the absurdity of pigeons steering missiles, the British took a far more pragmatic approach to avian assistance during the war. The British military deployed over 200,000 homing pigeons, not as weapons, but as reliable communication networks. Every RAF bomber and reconnaissance aircraft carried pigeons in watertight containers. If radios failed or aircraft ditched in the North Sea, the pigeons carried messages home, often saving the crew's lives. The British approach produced staggering results. Success rates for message delivery approached 95%, far exceeding radios vulnerable to jamming and atmospheric interference. Entire rescue operations were triggered by returning pigeons carrying coordinates from downed aircraft. Some missions became legendary. One pigeon named Winky, an oil-covered hen, flew 120 miles back to its loft after an RAF bomber crashed in the North Sea, arriving in time to alert rescue crews. The 4 surviving airmen were saved within 15 minutes of the pigeon's return. Another, Gustav, delivered a message from the Normandy beaches on D-Day itself. Allied forces maintained radio silence to avoid German detection, and no electronic communications were available. Gustav flew 150 miles against strong headwinds, carrying confirmation that the invasion had begun. His message arrived in time to prevent friendly fire incidents and coordinate reinforcements. Mary of Exeter demonstrated extraordinary resilience across 4 missions to occupied France. She sustained multiple injuries, including shotgun wounds, hawk attacks, and shrapnel, yet still completed her missions, earning the Dickin Medal, Britain's animal equivalent of the Victoria Cross. G. Joe flew 20 miles in 20 minutes to deliver vital intelligence that prevented a bombing run on Allied troops. Each bird proved the reliability and utility of biological systems, particularly in conditions where technology failed or was compromised. While the Americans attempted to weaponize pigeons, the British recognized pigeons' evolutionary advantages. Homing ability, navigational instinct, endurance, focus under extreme stress. Instead of forcing them into mechanical roles, Britain let pigeons do what they were naturally good at, find their way home and deliver messages. Their success was undeniable, and they were formally honored for it. The contrast between American and British approaches illustrates a key lesson. Americans, technology first, behavior engineered, absurdity tolerated only if authority approved. Pigeons could do incredible work, but human perception of ridiculous blocked adoption. British, practicality first, leveraging natural skills. Pigeons were highly effective in communications because planners understood their limits and strengths. By the early 1950s, Project ORCON ended, but the legacy of these pigeons lived on. In behavior analysis, shaping techniques developed in Minneapolis became standard practice in technology. Semiconducting screens and direct contact detection influenced early interactive displays and targeting systems. In military history, Project Pigeon remains a cautionary tale. Success alone is not enough. The perception of the technology, and whether leaders can accept it, often determines whether it is deployed. The pigeons had done everything asked of them. They tracked targets perfectly. They demonstrated endurance far beyond expectations. They were biologically reliable systems performing tasks far beyond their evolutionary purpose. And yet, in the end, their work was cancelled. The story does not end there, however, because the pigeon's legacy continues to echo in military research, animal behavior science, and even the touchscreens we use today. By the early 1950s, Project ORCON, the Navy's revival of Skinner's pigeon-guided missiles, was formally concluded. Electronic guidance systems had matured. Vacuum tubes were replaced with reliable circuits, radar became precise, and radio control could be protected against jamming. In practical terms, pigeons were no longer necessary. But the story of Project Pigeon extends far beyond cancelled contracts and government memos. Its legacy lies in psychology, engineering, and the subtle ways human perception shapes the adoption of technology. 1. The psychology of rejection. Why did Project Pigeon fail, despite working flawlessly in testing? The answer lies less in mechanics and more in human perception. Skinner's pigeons were technically perfect. They maintained attention, reacted faster than electronic systems, tracked moving targets under stress, and retained training for years. Yet, when senior military officers observed the demonstrations, their response was predictable: laughter. The absurdity of the scenario, birds inside bombs, pecking at targets, overshadowed the technical data. Engineers could see the mathematics, the physics, and the reliability. Generals saw only a spectacle that challenged their notions of serious weapons. This reflects a recurring theme in military and technological history. The tank was dismissed by cavalry officers who could not imagine horses being replaced. Radar was doubted by admirals who trusted human lookouts over instruments. The machine gun, despite its clear effectiveness, took decades to gain widespread acceptance. Effectiveness alone does not guarantee adoption. Leaders must be able to conceptualize success within their existing mental models. A pigeon-guided missile, no matter how accurate, broke that model in 1940s America. Skinner himself noted the irony with characteristic dry wit: the physics had won. The psychology had lost. 2. A legacy in behavioral science. One of the most enduring impacts of Project Pigeon was in the field of behavioral psychology. The General Mills Laboratory became a testing ground for advanced operant conditioning techniques. Graduate students who worked with Skinner, including Keller and Marion Breland, applied these principles after the war to train animals for commercial purposes. Theme parks such as SeaWorld Television and film production circus performances. The techniques refined during Project Pigeon, shaping complex behaviors through successive approximations, using variable reinforcement schedules, and creating decision-making redundancies, are foundational in modern applied behavior analysis. In essence, military experimentation directly catalyzed the professionalization of animal training, influencing industries far removed from warfare. 3. Contributions to technology. Project Pigeon also contributed indirectly to early human-computer interface technology. The semiconducting touchscreens used in ORCON to detect pigeon pecks inspired systems where operators could designate targets directly by touch. Reports from the National Institute of Standards and Technology note that these early touch input concepts were applied to radar pick-off display converters. This allowed human operators to interact directly with digital systems, a precursor to modern touchscreen devices. In other words, the idea that a living creature could manipulate a mechanical or electronic system helped engineers conceptualize direct input interfaces, decades before touchscreen technology became common in consumer electronics. 4. Lessons from the British experience. While American planners attempted to weaponize pigeons, the British took a pragmatic approach, emphasizing communication rather than weaponization. Homing pigeons were deployed by the RAF and other branches for message delivery, particularly when radios failed or were compromised. These birds saved lives. Success rates for message delivery were as high as 95%. Messages included coordinates from downed aircraft, intelligence from resistance networks, and critical wartime updates. Notable missions include Winky, Gustav, and Mary of Exeter, all of whom received the Dickin Medal, Britain's highest award for animals in military service. The British approach illustrates an important principle: use technology and biological systems for what they do best, rather than forcing them into unnatural roles. Pigeons excel at navigation and endurance. Americans tried to make them into missiles. The result was brilliance limited by human skepticism. 5. The technical achievement. Despite cancellation, the pigeons achieved remarkable feats. Tracked targets accurately for over 90% of simulated engagement time, maintained attention under noise, vibration, and extreme handling, retained learned behavior for years without retraining, outperformed early radar and electronic servo systems in key tests. These results make Project Pigeon a unique example of biological computation, an organic solution to a mechanical problem, long before the term bio-inspired engineering entered common use. The nose cone apparatus from Skinner's original experiment survives today at the Smithsonian National Museum of American History, a testament to this extraordinary combination of psychology and engineering. 6. Broader implications. Project Pigeon teaches several important lessons for technology development, even outside warfare. Innovation is often limited by perception. If decision-makers cannot imagine a technology working, even the best results may be ignored. Biological systems can outperform machines in specific contexts. Evolution has optimized organisms for tasks that challenge human engineering. Interdisciplinary collaboration drives breakthroughs. The combination of psychologists, engineers, and manufacturers in Minneapolis created solutions that neither could have developed alone. Legacy extends beyond immediate application. While the pigeons never flew into combat, their training techniques influenced animal behavior science, and their interface designs foreshadowed touchscreen technology. 7. The irony of success. In the end, Project Pigeon was both a success and a failure. A success because it worked. Pigeons guided missiles with precision greater than anything available at the time. They endured conditions that destroyed electronics, resisted jamming, and provided a fully operational guidance system. A failure because humans could not accept it. The image of a pigeon steering a bomb was simply too ridiculous. Authority, perception, and psychology, not mechanics or physics, determined the project's fate. Yet the pigeons themselves did not fail. Every bird trained earned its wings, some pecking over 10,000 times in a single session, performing feats that would be impressive for any machine, let alone a living creature. They were disciplined, reliable, and effective. And in their way, they were heroes. 8. Closing reflections. Today, Project Pigeon is remembered as one of the strangest episodes in military history. It challenges our assumptions about innovation, human psychology, and the potential of living systems. It also reminds us that sometimes the weirdest ideas are the most brilliant, even if they never make it into combat. From pigeons pecking inside missiles to touchscreens, behavior analysis, and even theme park animal training, the impact of this unusual World War II program continues to ripple across multiple fields. And perhaps the most enduring lesson of all is this: technology that works is not always the technology that gets accepted. The pigeons behaved perfectly. The generals laughed anyway. And history, as always, took notes.